Welcome to lesson 23, Damping, Resonance and Forced Vibrations. Here's a plan for today. A real pendulum doesn't swing forever. It loses energy to friction and air resistance and gradually stops. That energy loss is called damping. With light damping, a pendulum swinging in air or in a light fog, it still oscillates back and forth, but the amplitude shrinks a little each cycle, decaying inside an envelope until it settles. Crucially, the period stays roughly the same. It's the amplitude that fades. Now push the damping harder. With heavy damping, imagine the pendulum swinging in thick treacle or tar. It barely oscillates at all. It just crawls slowly back towards equilibrium, taking a very long time to get there. But between light and heavy damping lies the sweet spot, critical damping. That's the perfect balance, where the system returns to the equilibrium in the shortest possible time without oscillating at all. No overshoot, no wobble, and no crawl. The everyday example is car suspension. You want critical damping. Too little and the car bounces up and down after every bump. Too much and the suspension is effectively rigid and you feel every stone in the road. Critically damped, it absorbs the bump and settles instantly. Now, instead of letting an oscillation die away, let's feed energy into it. If you apply a periodic driving force to an oscillator, you have a forced vibration. Everyone has done this on a playground swing. You know instinctively that pushing at random does nothing, you're just fighting the motion of the swing. But push in time with it, at its own natural rhythm, and even small pushes build the amplitude higher and higher. Timing is everything. So what happens if we slowly raise the driving frequency and watch the amplitude? It climbs, reaches a dramatic peak and then falls away again. That peak is what we call resonance. It occurs when the driving frequency equals the natural frequency of the system. At that point, the driver leads the oscillator by 90 degrees, pi/2, which means it is feeding energy in at exactly the perfect moment in every cycle. Maximum energy transfer, and the amplitude builds enormously. And damping controls the shape of the peak. Add more damping and the peak gets lower and broader. The resonance is blunted because energy is being drained away as fast as it's fed in. The classic example is a bridge. If the wind, or people walking in step, happens to drive it near its natural frequency, the sway builds, and that can be catastrophic, which is exactly why engineers deliberately design damping into bridges, to lower and broaden that peak so the bridge can never resonate its way apart. That's the end of the video, and the end of the topic of further mechanics. Next time we start thermal physics, internal energy, the first law of thermodynamics, and how much energy it takes to heat something up. Thanks for watching, and check out my tutoring page below.